In this section we introduce the power supply rejection ratio. The ratio tells us how well an op-amp rejects the power supply ripple from getting to the signal output of the op-amp. So, this section is about power supply noise and rejection of it in an op-amp. We do not want the power supply noise to contaminate the output signal of an op-amp, so the higher the attenuation the better. We are familiar with this symbol of the op-amp. It is a 3-port device. It has a differential input port, 2 power supply connections make up the second port, and the third port is the signal output port. The power input port supplies power to the op-amp, but noise also enters the op-amp through this power, on both the negative and positive supply lines. An attenuated version of this noise appears at the output of the op-amp. The attenuation factor is known as the power supply rejection ratio, and the higher this attenuation the better. When designing circuits with op-amps, every effort is made to supply op-amps with the smoothest possible voltage. This is an example taken from an op-amp datasheet. The power supply rejection ratio is between 72 decibels and 85 decibels. This means the power supply noise is attenuated by a factor of about 1/10,000. Actually, the power supply rejection ratio should be negative because it is smaller than 1. We continue with our analysis of the power supply rejection ratio. In this slide, we explore how to model this in our equivalent circuit for the op-amp. This is the LT SPICE schematic for the op-amp equivalent circuit, with the power supply rejection added. The power supply noise is modeled using an AC source, V2. The output of V2 passes through an attenuation stage gain 2, that has a gain smaller than 1. The gain stage gain 2 is connected in series with the op-amp output, which means the attenuated noise is added to the output signal of the op-amp. The amplitude and frequency of V2 can be varied over a range of values, using the LT SPICE param command. If the power supply contains a specific range of frequencies that is unwanted, these can be removed from the output signal using a notch filter. This equivalent circuit can be used to model this. In this example, the power supply rejection ration is -60 decibels, or an attenuation factor of 1/1000. The op-amp open loop gain is shown as 60 decibels, which means it amplifies the differential input signal by a factor of 1000. We continue with the power supply rejection ratio. We add the power supply rejection to the complete equivalent circuit. This is where the power supply rejection circuit is added to the op-amp equivalent circuit. The rest of the equivalent circuit is the same, and to reinforce the circuit with the student, we quickly run through the different parts. Common mode rejection ratio. Offset cancellation circuit. Slew rate. Offset voltage. Double pole. Clamping circuit. Feedback resistors. And this is the end of the power supply rejection section. The next section is about the op-amp noise. This is the noise generated inside the op-amp.